All right. So welcome everyone to the third CAE seminar. And today we have with us, we are very excited to have with us Christian Steputat. He's a PhD student in the department. He is a licensed professional engineer. And today he's going to be telling us about how to use composite reinforcement to build resilient and sustainable infrastructure, which is a topic we are all very interested in. So Christian, thank you for agreeing to give a talk, and we are looking forward to you telling us more about your research.
Sure. Thank you very much, Louis. I'd like to thank Louis and Pranoy for moderating this whole entire fall 2021 seminar series. But I do have to start and begin with, before I discuss my talk on resilient and sustainable concrete infrastructure induced by utilization of composite reinforcement. I'd like to thank all my committee members, Dr. Antonio Nani, who is the chair of the committee, Pranoy Suraneni, Landolf Rodebabarigos, Dr. Qingdao Yang, and Dr. Francisco de Caso y Barcelo. So their help is very much appreciated. And of course, all the other faculty at UM whose discussions have been very helpful over the last couple of years. And a special thanks to Dr. Darren Ural and Edward Dower for having me interested in electron microscopy and sustainability engineering. So having said that, I'm going to move on to my discussion, and it's essentially what it will focus on. Hold on one second. What it will focus on is three different studies, of course. As we all know in engineering, in order to complete the PhD as a PhD student and candidate, for civil engineering, we have to include three separate studies that are interconnected. And the ones I'm going to be presenting on are shown on the screen right now. My first study that started off in late 2018 and extended all the way through 2019, the Florida Department of Transportation State Road A1A project, which is an innovative GFRP secant pile seawall, which was fairly deep for a seawall, since it's installed as a very visually pleasing wall. It's essentially buried, as you will see later, so you don't actually see it once it's completed. And it actually has an extended pile cap. What's unique about it is, we'll discuss momentarily, but it is fairly long. It was one of the first projects in Florida to be about 1.6 kilometers long, or 1 mile long. And it consisted of 1,847 pilings up to 40 feet in depth. And it's using GFRP extensively. We'll discuss that momentarily. That was my first of the interconnected studies. While the second one is going into the Ibis Waterway, or Northeast 23rd Avenue Bridge. And I'm discussing the superstructure as well as the substructure. And I'm especially looking at 18-inch by 18-inch precast, partially pre-stressed pilings that are reinforced with GFRP bars regularly, as well as additional coiled GFRP strands that were delivered from Italy. That was a first-time use here in Florida, and we tried to pre-stress them in accordance to Florida Department of Transportation standards. And then as the third part, we went into the implementation phase. We were trying to drive these piles without exceeding stress limits on the piles, and I conducted some pile dynamic analysis and some other studies in the field that we'll discuss momentarily. But these are essentially the three studies, and my research heavily will discuss, and we'll talk about that in a minute, the case-by-case implementation and practical implementation, because we found that there's a lack of data in the field, that a lot of the construction industry was hesitant to use GFRP just because there's maybe insufficient data out there in terms of fairly large example projects. And sometimes people look at design code implementations, which have progressed quite rapidly, as we'll discuss momentarily. But moving on to the first project, Hurricane Matthew came through in 2016 and impacted Flagler Beach, Florida. In the center here, you can see the hurricane, and on the right-hand side, where it moved through in 2016. And essentially, Flagler Beach is, if you picture nowhere else, it's fairly close to Jacksonville, Florida, for lack of a better location. But so it is on our east coast or northeast coast, and it's quite frequently impacted by major hurricanes and storms, tropical storm events. And you can see here on the left, like some pre-pictures of the destructive forces that resulted in a lot of the washout of State Road A1A. State Road A1A is also in Zone A of an evacuation route. So it's essential for emergency vehicles to evacuate all the people that live along the beach, as well as emergency vehicles that need to be able to travel up and down the state road. In the middle bottom here, you can see some of the washout, and I'll have more pictures to show in a minute, but you can see this is an evacuation route that's completely damaged and washed out. A couple more details here in this slide. You can see Flagler Beach, you can see the erosion, the washout of the state highway system, and the undermining of the roadway system, which should be a no-no because it's supposed to be an emergency evacuation route. What you will find, and we will discuss that in a minute, a lot of these areas and protective regions of roadway systems along, especially the coastal regions, are typically protected by some type of means of a seawall or bulkhead. And a lot of times in the older days, and we'll get into that in a minute, sheet pile walls were driven, sometimes for ease of installation, quick installation. But as you know, we're in a very corrosive environment in Florida, and high UV, not so nice environments in terms of corrosion that will be subjecting our structures to. So we find frequently that these were in place sheet pile wall systems. And essentially, you can see how they're all corroded through, and studies were done. And essentially, it was determined that the progression of the corrosion is so high that we will start losing the sacrificial steel, and no piles will have any sacrificial steel left in the next 7 years. So now we're going to look at alternatives to steel sheet pile walls. What can we do to be sustainable, resilient, and save on maintenance costs for the system? Now, before I go into details how it was installed and constructed, essentially what we have were some considerations. What kind of wall systems can we build? What kind of seawall bulkheads can we build that make sense? So there were 4 alternatives put on the table. One was a 36-inch or 3-foot diameter secant pile seawall with steel rebars. Again, steel rebars subject to corrosion, shorter service life, shorter lifespan, more maintenance. The second one was a 36-inch diameter secant pile wall with GFRP bars, which of course are basically twice as strong as steel, 4 times lighter, and we'll get to that in a moment. So they have some advantages, and of course they don't corrode, or at least not to the terms that steel does. They have some other criteria that we'll discuss shortly. The third one was anchored steel sheet pile walls, and then double cantilevered sheet pile walls. Double already throws up a flag. Double is twice as much. So your costs are anticipated to go higher. These numbers actually come from an actual bid that was done at the time the wall was proposed. So some of these numbers have changed over the years now that I've tracked, but essentially they were ranked. And as you can see, for all the ones of you that haven't done it, when you go through either city rankings, government rankings, or DOT rankings, they will rank projects and even sub-consultants. Of course, number 1 would be the choice they would like to go with. You can see here that the secant pile seawall with the GFRP bars was selected as the best overall alternative. Some of the reasons given were, of course, it's corrosion resistant, the ease of installation, it's lighter, it's stronger, and what had to be considered were the geotechnical soil conditions. We have a lot of coquina rock. For the ones of you that don't know, it's almost like a shell-like substructure, and it's very difficult to drive sheet pile walls successfully in coquina rock, especially since we also have buried boulders from some type of riprap work that was done for shore protection. So also the noise from driving sheet pile walls is sometimes excessive, the clanking and banging sound on the steel. And it's a very community that's very involved. And of course, they want to protect the community. So we want less vibration, less noise for noise pollution, less vibration pollution, and of course, an efficient means of installing them successfully. Having said that you know the 4 choices now, this is the layout. We're looking at segment 3 on the left. On the right side, it's written there in red. It's about a 1 mile or 1.58 kilometer stretch where we are going to install that secant pile seawall, which was the main area of washout. On the left, you see the Army Corps of Engineers had a renourishment project in place as well for what they call a high vulnerability area, but that is a subject of another paper. I'm not going to go in detail on that. We're going to concentrate on segment 3. On the right here, you can see a schematic. You can see on the right there the basically buried secant pile seawall. And what's unique about it is it's driven. It's you know 1 mile long, 1.6 kilometers. And eventually we're going to build a dune across the top and renourish the dune system, staying within the right-of-ways, which is essential for DOT, as well as basically bypassing turtle nesting areas, which are one of the environmental considerations. Basically, our seawall system, you can see in the middle picture, it's about a 40-foot long GFRP pile. On the right, I'm not going to go in detail on it. It's just a simple layout showing the cages. I'll have more pictures to show you. It makes more sense than just the data. And then we have a pile cap, a 4-foot wide pile cap that's continuous across the top, tying all these piles together. These are interlocking piles, which means they overlap by about 4 inches. To make it essentially watertight. It's not meant as a cofferdam, just to make it a tight wall system that's interacted and coupled. Now, you can see here some of the pictures of the construction as we were constructing these on field, and I spent about a year on the field documenting the pitfalls, lessons learned, and hopefully some white papers that will come out of it. In regard to the found studies, including some motion time studies and efficiency studies I did as well. So basically you can see how they assemble the cages, and you can see on the right here where they're lifting one of them, and you can see the flexibility and lightweight of them. And bottom right next to Flagler Beach sign, you see the toe assemblies. My hope was to eliminate the toe assemblies because they're very costly. And they technically weren't needed based on my inspections on the site, but it was a decision made that for this project, we will maintain the toe assemblies just because it would require engineer of record review, a delegated engineer, and it would have delayed the project by probably at least 6 weeks. So on the next project they were going to do, and hopefully will do in the near future, I'm trying to eliminate the toes, which would be a tremendous cost saving, and it's not needed for the type of soils we encountered, which consisted of the coquina rock and silty sands. Now, the toe ends we just discussed, we did have wet insert bars, and I'll discuss that momentarily. The pitfalls that we had, everything is wire tied, of course, with coated ties. They're not steel, so again we're looking corrosion, and of course they're quick and lightweight in nature. Needless to say that we had to do some type of QA/QC testing, and as part of the engineering I've done over the last many years, I'm also a licensed inspector in Florida, so I lent a hand in the QA and QC work in the field. I did a lot of the quality control testing in terms of concrete and fluidifier testing in the field, as well as involved in the lab. This is what we actually tested in our UM's advanced construction materials lab for the lot sizes. And we are required to take lots to ascertain that every delivery that came to this site was adequate and okay. And we did have a lot of the deliveries come from Canada. So we needed to make sure everything is fine, because otherwise it would have delayed the projects if we needed a new delivery. You can see on the right here the Florida Department of Transportation requirements, and then the lot 1, 2, 3, and the mean that everything exceeded the minimum criteria. And I do want to refer you to the bottom, the tensile modulus of elasticity, which is in the range here of from 7,600 to 8280, which equates to about 46 to 56 gigapascal. And we'll talk later a little bit about the advances in higher strength moduluses, which allow us to get closer to a one-to-one replacement of the steel. Not quite one-to-one, but we're getting closer. Now, installation of the wall was achieved by 2 means. First of all, we had to install a guide wall. Why do we do a guide wall? If you haven't seen it, it's a template, a steel insert. On the third picture here, we are basically pouring concrete, very low strength concrete, that's holding it in place and forming those 3-foot diameter circular openings. Well, the reason this was done is because we have tolerances to adhere by, and each of our drilled shafts or secant piles had to be within a ½ inch tolerance, 1/4 inch in some. So this would give us perfect vertical alignment and ensure a 4-inch overlap. You can see from left to right installation of the trench boxes, the concrete pouring, and then the removal of the steel, which would lay us out with the perfect locations so that everything is certain to be in the right locations and in the right alignment. On the left, you see a drill rig. We actually constructed a specialized drill rig. It was started off as a Bauer rig, originally from Germany. It was modified in California and shipped here for this project, which was modified and very efficient. We were able to build 1 mile, 1.6 kilometers of seawall in about 4.5 months, complete with dune restoration. So it was very little impact, a little in quotation marks, but relatively minor impact to the community, and resulted in a very cost-effective, efficient project. You can see here some more of the cages and basically the site pictures. So having said that, on the left here, I did talk a little bit about it, that they're 36 inches in diameter on those secant piles. They also have 25 number 8 GFRP bars and 1 number 8, which I consider a tension bar, not technically, but it's a center bar that's installed in the middle. And then we do have helical loops and the toe assembly here on the left. On the right here, you can see the slurry. Essentially, we will drill this hole, as the middle picture shows, with the drill rig, drill the hole. When the drill is all the way at the bottom, we inject a slurry with a fluidifier, a moderate fluidifier, and basically come up, trimming back out the hole. And then once it's all stabilized with Y, because we got to stabilize the hole, preventing it from cave-ins, and then we will insert the steel cage here on the left. This is a sequence of installation. You can see how it happens. These were on the left, I'm going from left to right. These were the pre-assembled cages that were brought to the site. We just assembled them across the street. They're very lightweight in nature, so we brought them over. They were lifted in place in the second picture. Remember, we have 1,847 of those. Third picture, you can see how it's starting to go in the hole. We lifted it, of course, with a crane. And the important part here is that I do need to mention the Florida Department of Transportation does not allow, and I repeat, does not allow for mechanical means to basically push the cage down. Now, we didn't know much about this, if it would work, if it did not. So a lot of new information I was able to record, which hopefully will be helpful for future projects. But the first question was by the contractor and everybody else, will these cages float? They are 4 times lighter than steel. They are GFRP, they are not steel. Density considerations, the fluidifier makes it more fluid. And make a long story short, we did not need mechanical means. As you see in the fourth picture on the right, we essentially had 2 people, maybe sometimes a third one, guiding it down. Occasionally they did step on some of the hoops to give it the final push, which is allowable, but we did under no means use either the crane, drill rig, backhoe to push this one in the ground. So once we pushed it all the way to the bottom, it actually remained in place. We did not have to build a saddle. I had envisioned we had to build like a weighted saddle to hold it in place from flotation or drift. But it worked perfectly. It had to stick out 1 foot, 12 inches, and it remained in place when we pushed it down. So it was very successful, and we could demonstrate it's not needing a saddle for drift protection or flotation. I'm not going to go too much into the grouting and fluidifier verification that I have done so far on the project. The decision was made that since I'd have so much data that I accumulated in the field for the quality control testing I did, from concrete cylinders to fluidifiers, I actually was able to do some scanning electron microscopy testing on both GFRP bars and some of the other items in terms of concrete, grout, aggregates. But the decision was made, since not everything can be in the PhD dissertation that I need to defend. I will publish future papers on it, hopefully after I graduate with my PhD next year. And I would love very much if the faculty was involved, the same faculty I'm working with now. And I'm very interested in continuing with this research to some extent, basically to show the documentation. You might ask, what is the reason? You have a lot of work done. Why wouldn't you use it? I think it's for all of us PhD students. Questions could be asked when you defend this. I only had one fluidifier on the side, and it was a moderate type fluidifier and one design mix. Well, if I would have to defend it, I think I don't have enough data. I certainly can defend what I did and how I did it and that it's good. But how would I stipulate different mix designs, different conditions? I just don't have enough data for it. So it will make an interesting paper, but it was decided pretty much to leave it out of the dissertation since only 3 studies are needed. Now, giving a quick recap on this, on the left-hand side on the top, you can see the guide wall that was unreinforced, the low-strength concrete. And what was done, it was required by the Environmental Protection Department and the city to remove anything that wasn't part of the permanent wall for environmental considerations. There are turtle nesting grounds, there's other concerns, possibly adverse mixed design considerations in terms of chemicals that nobody really looked in detail at. So it was all removed and discarded. My hope for the future is that somebody else will pick up on this research. I would love to be involved, but it seemed like a lot of waste. Remember, we did this just on this project for about 1 mile. I think the phase 2 of this project is proposed for 22 miles. It was supposed to happen, be initiated towards COVID. Of course, COVID happened. So I anticipate this hopefully happening in the next few years. But it would be nice to be able to utilize this. And Landorf, if you're listening especially, maybe we can use some of that for sunken reefs somewhere if we can use a mixed design that doesn't have chemicals in it. I think it would be worthwhile to just move it and use it as artificial reefs rather than discarding it and using it for landfill, maybe recycling. But again, you can see the progression from left to right, building the cages, the original alignment, the caps that essentially got poured, the continuous cap, and then the dune re-establishment on the right. So you will see nothing of that wall at all. Now, a quick in terms of some life cycle costing. I'm not going to go in detail. It'll be a follow-up paper that I'm working on for this semester. But essentially, what was done during the bid stages, it's of course more expensive to use GFRP, which would be a reason for most contractors to say, no, we don't like this option. But that shouldn't be the end of it, because you typically have a 50 to 75-year life for traditional reinforced concrete, while with GFRP, we know we have at least 100 years. And in my opinion, the 100 years is a good number, but it is, of course, subject not to the GFRP. I think for me, it's more of the aggregate what we're using. If we're using the lime rock or granite, there's different characteristics for those that need to be researched further. But basically, extrapolating this over the 100 years, you actually end up with an 18% cost savings over the lifespan of the expected wall. That was one of the reasons DOT chose it. And that's without the maintenance costs and environmental benefits that need to be considered for the corrosive and aggressive environment we have in Florida. In terms of this wall, the original budget was $27 million. Low bid was around 22 million. So it was about $4.5 million less than what was the willingness to be used. Now, to sum this one up and moving on, there are some pros and cons, of course, and lessons learned. These are just some. There's going to be a more detailed list next year that I'm compiling right now. But of course, we use it for seawalls, piles, and piers. I will talk about the seawalls and bridges in a little while. Marine structures, quick installation, lightweight, assembly time savings, and I'll get to that in a minute. I did some motion time studies. Part of my engineering background is industrial engineering, so I was involved in a lot of motion time studies and other studies. So I was very interested in that as well. To or no option we discussed. The GFRP cages remain in place, so no flotation that we could prove, no drift, and resilient, durable, and extended life cycle. Now, what are the cons? What are some of the negatives? Well, bend shapes need to be manufactured or fabricated. You cannot bend anything in the field, which for this, obviously, we really didn't need. It's pretty much straight secant piles. We had some bends, some U-shapes for the continuous cap, but no unusual geometric shapes, which, by the way, can be done, just got to be pre-planned. A little bit of itching, skin itching was reported. It is glass fiber overall, but people found out real quick how to handle that. Everybody enjoyed that it's 4 times lighter than steel, which we're going to discuss in a minute. And basically, it's a definite alternative to black steel that corrodes rather quickly. Now, some of the other benefits as validated by this project, essentially the economics, right? The return on investment. But it has to be said that it is higher on a life cycle cost analysis basis initially, but you have to look over it like we just established over 75 to 100 years. You're actually going to be better off, less maintenance costs. GFRP is anisotropic and linear elastic up to failure, as everybody knows. And current specification and design guidelines exist and have been improved drastically. So it's getting a bigger foothold in the construction industry, which is nice to see. We just got to, in my opinion, push it with more case studies, field data, that people accept these more readily and are willing to use it. Lightweight, of course, high tensile strengths and other characteristics that apply for the service life of the structure. Now, I wanted to talk just a few minutes here in regard to the studies that were done in terms of savings. I do need to mention again that we did install 1,847 secant piles, and no alterations were needed, absolutely no modification. It was beautiful, it went in place, no changes needed to be made. It was a very successful project. It was relatively quick installation. As I said, it was only 4.5 months from start to finish, which is relatively quick for a project of this size. And what I found on site, the main time that needs to be considered is the delivery schedule of the concrete companies. Where are they located? How far from the plant? How quickly can you get all this concrete there? And that was the main holdback. We could have done more efficient work if we had quicker, more concrete readily available. So if that can be scheduled and planned better, for all you industrial engineers, a lot of scheduling there. If that can be done nicer, it would be progressed even better and even more efficiently. Now, with two assemblies, I'm not going to talk about. The noise pollution was a lot less. I actually installed vibration and noise monitoring equipment across the street and basically recorded the data to see if it was within decibel levels acceptable to the city, which it was, and it was a lot less than what I've experienced on other sites from driving sheet pile walls. So that was all beneficial. Now, moving on, we don't have that much time in this presentation. I would love to talk a lot more, but I want to keep it on time. So moving into the second and third study that I've been doing for my PhD project since the fall of 2018. It's the Northeast 23rd Avenue Bridge, or the Ibis Waterway. And also I will discuss the precast, partially pre-stressed GFRP piles. And it was a GFRP RC, reinforced concrete seawall innovation in regard to constructability and adaptability. The three parts we're going to consider are pre-stressed and driven GFRP piles. And as I mentioned, I was on site for about 1.5 years with an NSF grant as well. So my appreciation goes out to that. And of course, the university for enabling that work. The GFRP, the second part, is the CIP, or cast in place end bends, intermediate bends, and bulkhead caps, which were also innovative. And then, of course, it's the first soldier pile bulkhead seawall with GFRP RC precast panels that was done in Florida. So another first. I was lucky to be involved in 2 projects which were considered a first in Florida. Now, from left to right, really quickly, we are looking at basically our pilings up to about 55 feet in length. We did some of them between 40 and 55 pilings. Middle picture here was the initial picture of basically doing pre-stressing. On the right is a typical cage construction with instrumentation. And of course, it's the Ibis Waterway. To give you a schematic, this is what it looks like. We have a CIP, cast in place flat slab. We have CIP caps, precast panels, and also pre-stressed or partially pre-stressed pilings, and also a relatively innovative seawall, which was precast out of GFRP entirely. And I'll go into all that with some pictures momentarily, since I felt it's better to demonstrate in terms of pictures instead of just data sets, which I am actually presenting later on in one of the papers I'm about to finish writing. But having said that, what we did, we had some, or Dr. Nani had some connections in Italy. So we have some on the left, I'm going from left to right. We had some innovative coiled GFRP bars that were delivered in coils. and it had some videos how to uncoil it. However, uncoiling the video we got was basically put the coil on the ground, cut the ends, and basically jump out of the way and let it uncoil rapidly and release stress, and it would uncoil very nicely in the video. Well, unfortunately, in the field, we don't have that situation. We don't have concrete or asphalt. We have at best gravel, a lot of times soils. We tried one, the end will catch and it will kink and break the bars, so that doesn't work. The middle picture here with the spool, with the yellow, you can see the kinks in the cable. Of course, when it does that, we have to throw away the whole spool because we need this to be continuous, right? We're going to pre-stress this in a pre-stressing bed that's 480 feet long, 440 to 480. So that didn't work. You can see some of the fractures in the middle two pictures. And also it was difficult. We had originally a pre-stress manufacturer in South Florida. And so we mobilized to the site from Italy. All the coils were delivered. Everything was there. And of course, there was hesitation about the dangers. Nobody had done GFRP to that extent before. If it breaks, OSHA, safety requirements, everybody knew what to expect from 7-strand steel pre-stressing. Nobody knew about GFRP. So make a long story short, the company shall remain less. We do appreciate the help we got to try this. But essentially, they made the decision not to continue with the work. So on the right here, you see our picture where we packed up our good truck that we have in the lab. So we loaded up all the coiled rebars and had, of course, some big 18-wheelers come in to move all the other materials. And we found a different pre-stressed part in Jacksonville, so which required going up to Jacksonville. And I'll talk to you about that in a minute. So in Jacksonville, if you know about precast, there is Gate Precast. Gate Precast is a very good company. There's a lot of pre-stressing and they were super helpful. So if they see this seminar by any chance, a big shout out to them. Mr. Newman out there with the whole crew, we really appreciated all the help. It was just a fantastic working experience, and letting us build the cages there was phenomenal. And all the help they have given. On the left here, you can see the cages, and I do call it partially pre-stressed pilings that we drove on the site, because you can see here, these are regular GFRP bars that are not pre-stressed, that build the basic frame. And later on, and you can see it on the right picture at the bottom where it's being lifted in place. And on the top left picture here, you can see, I don't know if you can see them, look at the slightly different color, little bit thinner tendons or GFRP. They're a little bit more orangish brown looking there. They're not the type of green, but those were the pre-stressed coil GFR bars we inserted, and you can see them in the top middle picture here. There's actually one missing. If you count from left to right, there's one hole where we still have to insert yet one more pre-stressing cable. The biggest issue we had, these GFRP coiled bars are intended as some type of friction bars. Friction bars, I mean, they have a surface coating that's sanded, sometimes out of glass particles. It's a sanded finish. It's supposed to provide almost the equivalent to the black steel rifling, which provides additional friction when it's bonding to the concrete. Well, the issues we had with this, pulling them through the wood bulkheads removed all the sanding of it, or the what I consider friction help. And it became an issue because it also rained on site, and I'll go into that briefly in a minute. But you can see bottom right, our first approach also was to roll them all out. And this was the coiled bars, of course, not very efficient, right? You're going to have several hundred feet behind the stressing bed to insert all these cables. So it was a first try, since it hadn't been done before, but at least we got it inserted. On the right here, you saw a modification that I ended up doing to the pre-stressing, because we had special chucks with plastic grippers so that you don't damage the pre-stressing with the steel grippers. Problem is, we had 2 days of rain, and a lot of the sanding and glass was removed, so they were pretty slippery. So, and we had a couple of them break and slide out. So I ended up installing a regular steel gripper behind the plastic gripper just as a backup. And we were able to stress the cable successfully with that second one in place. Not an ideal connection, but it worked for what we had to do. We only had a finite amount of coil GFRP bar. We could not afford to break any, or we wouldn't have been able to do this project. Real quick in terms of concrete. In terms of concrete, what we have is Gate is amazing in terms of having their own batch plan, top right. So we have concrete on site. Bottom right, specialized equipment with a conveyor belt, front end funneled placement system. And of course, we vibrated everything in place carefully not to damage the GFRP. So that was very effective, efficient, and quick. In the top left picture, if you look closely here where my mouse cursor is, you have some coiled GFRP. Even on the left here, it was one of them that broke when we stressed. And again, it was a slippage type of failure. We had to remove that coiled GFRP and basically install another one. And then the pile driving we'll go into detail in a little bit. Now, this is the bridge structure when we initially started. On the left, the steel there is the template. If you haven't dealt with bridges before, we had to build a steel template to set the guides for the piling system that was driven. And you can see here the pilings that were driven. Unfortunately, we had a lot of severely differing site conditions. So we had very hard soils and we had very loose soils, which made it very difficult to drive. And you will see that in some of the pictures in a moment for different pile lengths. You can see the hammer in the top middle pictures, the red one. You can see here 55, 50, those are our markings. What is important, we had such dense soils, we would have damaged the piles driving. So we needed to pre-drill to an elevation of -39 feet in order to start our driving, because as you all know, for deep foundations, we have a minimum amount of embedment that we need, as well as a certain load. In this case, these pilings only, it's a relatively minor bridge, only requiring 200 kips per pile. 200 kips is not very much, 200,000 pounds. So we did run, I looked at pile dynamic analysis while we installed them, especially since they are GFRP reinforced, some of these, and pre-stressed. And we basically had to keep our driving stresses within the DOT limited range in order not overstressing the piles so we could use the piles. On the right here, if you look closely at the bottom 1, 2, 3, 4th line, you see two numbers, 1,022 kips, 1,008 kips. So I made the decision, since I was looking at the driving characteristics, we basically stopped. A lot of these piles only got driven 7 to 9 feet. That was all, because we already had 1,000 kips. Remember, we only need 200 kips. We didn't want to overstress. We already have 5 times the capacity we needed. And it gave us a successful installation of the first GFR pre-stressed driven piles that we could say, yes, we're not overstressed at all. Top left, to make it quick, and I'm gonna speed up a little bit so I don't run over time, my apologies. But you can see all the different pilings, how they're sticking out. That is quite normal if you haven't dealt with piles. We just hit very hard soils, different soils. So we are strictly looking at capacity for most of these. I basically cut off the driving between 750 kips and 1,100 kips. We only needed, again, 200 for some of these. So it was definitely, above what's needed without damaging the piles. If some people drive too much, you could say, well, you could have got 2,000. Well, not really, because you're inducing driving stresses that will crack the piles, and you're causing more damage than good. And you can actually shear the piles off underground and drive the top portion of the pile next to an existing one, voiding the pile requiring more corrective action work. So that wasn't warranted. On the left here, it gives you a picture of how high they were roughly. I took a picture down where we installed all these. And then on the bottom right, just so you have a quick idea, I did install vibration monitoring equipment on the ground, and I had readings which were less than a quarter of the maximum required or desired, so that we could ascertain that we don't cause any damage to adjacent houses, or if there was a liability claim, we could say, hey, not so fast. Measurements were taken, they were only a quarter what's allowable, so no way you have that kind of damage. It was more of a protective measure. Now, getting towards the end of my presentation, I do need to address the seawalls real quick. These were what I mentioned at the beginning of the presentation, the precast seawalls. They were made in Homestead, Florida, and shipped to Lighthouse Point, and they're entirely made out of GFRP. some steel lifting hooks that you see here. If you're saying, well, it doesn't all look like steel, they were all cut off and grouted. In the future, I hope they use something different than the steel lifting hooks, but that's another item that we need to look at. The bent bars, no damage, except I think 2 bars. We ended up drilling and providing a corrective action detail next to it. These come in panels. We see on the bottom right the black sections where we actually concrete grouted them together, so it becomes uniform. And then looking from left to right, basically, you're seeing the installation of the bridge for the intermediate bends, from pouring the pile caps all the way here. And it's going to continue. I'm going to go to the next page so you have an idea how it looks like, how deep they are, how thick. Again, it's a moderate to medium traffic bridge. It's not your high level bridge that would have deeper beams or bends. What we did have to have issues with initially, we could not install our temporary support system to build the deck because they were dredging, the city was dredging the waterways. So you see in the middle picture there, the dredge that was providing a deeper channel. And I get to that in a minute. We had to work with a lot of riprap for basically protective measures and scour protection. But you can see here, all these are GFRP bars, different types. And so they were all installed, and they were actually in 2 different dimensions, which was tricky because we had in and out of plane bending, which required bars to be cast since we can't bend them on site. On the left here, real quick, we essentially have steel supports, which is going to be going, you see here our substructure in place, and we're going now to the superstructure, which is our deck. A requirement for the DOT is that the seawalls and end bends, or the end sections on each of the ends, get tested. Since we had tiebacks. Tiebacks are, for lack of better words, in this case, were diagonally 40 to 60 feet long installed systems that would tie back the end bends, preventing the walls from moving outwards towards the water side. On the top right, you can see the specialized rig, which drilled these in and grouted them, but then I was able to record some data. It is required for DOT that we have creep and deflection testing equipment to see that those seawalls don't move any further than they need to. So all that was recorded over a period of 72 hours and basically recorded. And it was all found that it was within specification and accepted by the DOT. Now for the superstructure, you have a screed on the top left. If you haven't seen it before, it's self-leveling. On the bottom right, it's the front end of it. It has basically helical augers that basically, it's very unique. It's placing the concrete as you go, requiring a lot less labor. It has a vibration mechanism behind it, and it vibrates it for the top 2 3/4 inches. Well, you're going to ask me, well, you have a 12-inch deck, only 2 3/4 inches. Yes, but we do have the people that are placing the concrete having vibrators to vibrate the deck below it. This is just for the surface damage, since we don't want to damage any of the GFRP bars due to excessive vibration equipment or traffic on it. I did also install what I call here maybe a little bit inaccurate structural health monitoring sensors. They essentially are supposed to be, but it's more of sensors monitoring the concrete compressive strengths, temperature, humidity, and other characteristics for the concrete. These sensors, I installed 20 sensors. You see them on the left, and I go in a little bit detail in a minute here. You see it in the top middle picture. And essentially, these allow us to record data for a minimum of 60 days. Mine actually lasted about 64 to 67 days. For DOT, if you don't know, we typically run 2, 7, 14, 28-day concrete breaks. And if 28-day break does not come up to the minimum required, in this case, 5,500 PSI, we usually run a 56-day break. By having these for 64 and 67 days, with my cell phone, I could just go there and get all the data, knew what strengths is about what temperature, knew what area was hot, which one was not, where there was more wind circulation on the outer edges. And that was meant to look at crack propagation later to determine a little bit more reliability issues. Now, lessons learned from this, of course, is you got to be aware of your basically in-plane, out-of-plane bending, and you also got to anticipate some of the bar breakage ahead of time. So order your bars ahead of time because it can have sometimes longer lead times than steel rebar. Installation efficiency was about 52% better than using steel, or faster, less labor required, less tired workers, possibly less OSHA required accidents, and basically splices could be made. Constructability and adaptability was proven, and there are specification and design guidelines out there, so that was very beneficial. So it was, and we of course showed that partially pre-stressed GFRP RC piles were successfully driven, stayed within the required driving stresses, and can be used for these projects, which is exciting news. Now, a couple of other quick things. I've got 2 more slides before I wrap it up. I was able to, and we talked at the beginning of the presentation, how a PhD program can morph into some different aspects. I was lucky to be involved in an NSF fellowship that will actually run until December 31st this year, which allows me to work on additional seawall projects. And one of my projects that I'm going to incorporate as part of this PhD dissertation hopefully will enhance it. Not to show a separate study, but just show the feasibility in terms of case studies to present it to the construction industry, that hopefully people don't shy away from GFRP bars in the future, just embrace them and use them as a technological advancement. This is a seawall in the city of Charleston, South Carolina. It's going to be several miles long. We finished phase 1 in January. We are in phase 2 right now, which I've been out to the site numerous times, and it's anticipated to finish at the end of January, beginning February next year. So I will be there for the inspection work and some of the things that we are trying to change and make better. And then I'm currently working on a phase 3 together with a contractor and design engineering team, which basically would give an alternative, and we have to present that in the next 2 to 3 weeks. At the moment, the bid documents are only for black steel rebar. We want to change that to use the GFRP bars. So we have about 3 weeks to present our proposal to come up with an alternative, which we will present to the South Carolina DOT. And hopefully contractors will embrace it, they will use it, and it will make it more resilient and sustainable over the future. Having said that, I've got to add one thing. The Army Corps of Engineers is, of course, also involved. And typically here, studies were done in regard to sea level rise. And one of the requirements for the seawall is that it's got to be adaptable immediately with very easy corrective action, if you want to call it that, in the next few years, that allows for a 2.5-foot height increase for accommodation for possible sea level changes. And that goes up much higher over the predicted next 50 years from a reliability standpoint. But so the design will incorporate basically an ease of extending this wall up vertically by designing the foundations properly right now and reinforcing it accordingly, so that nothing else needs to be done except the height extensions included. And again, I'm working on the QA/QC inspections for the phase 2. As a last slide and to wrap up, I hope to be involved also as part of this dissertation in GFRP innovation and technology transfer for mainstream use, as I mentioned, make it more acceptable to the construction industry at large, make people not afraid to use the product. And I was actually lucky. These are some of the pictures I took for Seawalls in South Florida. And of course, as you all know, they are in various degrees of deterioration. A lot of these have been built 60, 70 years ago. Nobody did any maintenance. We have spalling, we have corrosion, and we have, most of them are seawalls. Some of them are actually seawalls connected. On the right-hand side, you see jetties or piers. And on the bottom left side, you can see the substantial corrosion that's happening by using steel rebars, which would be so nice to use a GFRP material or something nicer with correct cover protection, that we don't have these conditions occur in the future. I'm also working through OC and NSF fellowship, basically trying to help push using different DOTs accept GFRP bars in their bridge barrier systems and superstructure deck structure. And we are hoping that in the next few weeks or months, the Ohio DOT, South Carolina DOT, and Maine DOT, as well as of course FDOT that's already doing it, that they embrace this technology and start recommending the use of it, at least for some trial projects, and if they like it, hopefully implement it in the future. And with that, my presentation will end on resilient and sustainable concrete infrastructure induced by utilization of composite reinforcement. And I'd like to open it, put it back to Pranoy and Lewis, and open up to any possible questions or any questions you have in regard to the GFRP use.
All right, thank you, Christian. That was very interesting. So we'll open the floor for